All right, so graphing our trigonometry stuff, our unit circle. Here is the first graph that we're going to do, the coast graph. I like to think of coast graphs as starting at a maximum. Sometimes they're moved left, right, up, and down, but a coast graph starts at a maximum. Its domain is everything. Its range goes from -1 to 1. It has a period of 2 pi, an amplitude of 1. And the general equation for all of the zeros can be written like this. Start with one of them, which is pi over 2. And if you wanted to write them all, notice that there's a pattern in how much you have to jump to get to the next one. You either have to add pi, and then if you added pi again, you'd get to another one. Then if you added pi again, you'd get to another one. Or you could go backwards and subtract pi, and that's what this plus pi k means, right? Because we say that k is an integer. That tells us that we can add or subtract pi as many times as we would like. And of course, our y-intercept, that's easy to see that that's at 1. For our sine graph, domain and range identical. I like to think of a sine graph starting in the middle. I don't say start at 0 because sometimes it's moved up and down, right? I like to say my sine graph starts in the middle going up. Because sometimes in the middle it goes down. So normally a sine graph here starts in the middle of your graph going up. Still has a period of 2 pi, still has an amplitude of 1. And now if we look at the zeros, well, if you started at 0, and again our jump plus pi, jump plus pi, or we could subtract pi. So again, we have this pi times k, and the y-intercept is, of course, 0. And then finally, our tan graph. It has an awkward domain. And our domain for our tan graph is that x can't equal pi over 2. Range is everything. X can't equal pi over 2 plus pi k. And you notice that those are the zeros of cos because you might remember the identity. Well, here, I'll write it this way instead. You might remember the identity that tan of theta is sine of theta over cos of theta. And if you're not allowed to divide by 0, it might make sense that wherever cos of theta is equal to 0, tan of theta is not going to be allowed. And sure enough, those are all of your asymptotes. The big difference between sine theta, cos theta, and tan of theta is the period of tan of theta is only pi. It only, like, if we label this as negative pi over 2, and this one as pi over 2, the distance in between those two asymptotes is pi. And the graph repeats itself every pi units. Some people think that it looks a little bit like the x cubed graph in the middle, right? Kind of, but now we talked about in our earlier that the x cubed graph actually flattens out because it has a multiplicity of 0, it flattens out. The tan graph doesn't flatten out in the middle. So just a sort of like now you're advanced math students, you're like, I can notice some more of those details of what makes them different. Y-intercept is 0. There is no amplitude, undefined. And the equation of the zeros, well, wherever tan is 0, sine has to be 0 as well. So your zeros of tan are identical to your zeros of sine theta. And the general equation of the asymptotes is very connected to your domain. Those are just the zeros of cos of theta. And since we've been learning about odd and even functions, sine and tangent are odd functions, while cosine is even. Remember, an odd function, if you take half of it, so if I take the right half and do a double flip, if it matches up to the left half, you have an odd function. Imagine flipping it over the y first and then flipping it over the x, it matches up perfectly. An even function, you just have to flip over the y. If it matches up, then it's even, and that's true for cosine. You also learned how to sketch these, and some textbooks have H and K. Last year you probably had, you used, I think it was capital letters last time. Now they're going to little letters. Does that throw you off? Are you okay with changing parameter letters? Okay. What I like about the a sine b x minus c plus d is for those of you that were in my grade 12 class, we talked about the order of drawing sine and cos using a technique called DAB-C, which basically means you can draw your d value, which is your sinusoidal axis, first. You can then use your amplitude to find a maximum value and a minimum value. The b value helps you calculate your period, and then finally you can draw it with the shift. Some formulas to remember: that your b value helps you find your period because your period is always 2 pi divided by your b value for sine and cosine. For tangent, it would be pi divided by your b value because tangent has a different period. And your amplitude is always positive. So if there's a negative out in front, that doesn't mean your amplitude is negative, but your amplitude is always your a value, but just the positive of it. Okay. So, if I was graphing this using DAB-C technique, I would start, and I have the whole graph here, so I would start first with the minus 2. I'll overlap it in red here. I would do this thing as my very first thing. I know that my sinusoidal axis, the middle of my graph, is going to be at minus 2 because it was shifted down 2. Next, I would use my amplitude, which happens to be 4, to label a maximum value. I'll do this in blue. My maximum value is at 2. My minimum value is at minus 6. That would be the next thing that I would just label. So your vertical shift will move your sinusoidal axis, and then your amplitude will tell you how high and how low you go from there, so you can find your maximum and minimum easily. My period in this case is 6. Based on my b value, my period is 6. So what I like to do is I like to label 6. I'll overlap this in purple. I'll label 6, then divide it into 4 equal sections. Those sort of are like your 4 quadrants on your unit circle. And once you have those 4 sections, I would draw the graph temporarily. In this one, there's no shift, so the temporary graph is going to be my final graph. But where does a sine graph start? Sine graph starts in the middle going up. So that's why on the graph here, we're starting in the middle, and we're going up. Then each of these 4 sections that you broke your period up into, then it will switch from middle, first one, maximum, next one, back to middle, next one, down to minimum, and then back to the middle again, to draw one full period. So we divide it into 4 equal sections so that we can jump from middle to max to middle to min, back to middle again. Now usually I draw that with a dotted line, the dab C with the dash in there. That dash actually says, quickly just draw out the dotted line, and then deal if you have any shifts after. But in this case there was no shifts, so the dotted line and the solid line end up being the same thing, and we get the graph right away. If you want more, if you like this idea of the dab C and you want more in-depth stuff, you can probably type dab-c into YouTube, and one of my grade 12 more extended videos would probably show up. I don't know. I'm curious. Check it. So, second example. Ooh, it's in degrees. Controversy. 2 years ago, or was it on your exam last year, that they had a graphing one in degrees? People didn't like it. Right? So now instead of your period being 2 pi over your b value, your period would be 360 degrees divided by your b value, which is 120 degrees. And we have to graph at least 2 periods. So again, if I was graphing this, the very first thing I would do is I would draw my sinusoidal axis at y equals 0, because there's no plus anything afterwards. As far as dab C, I would look at my b value, which is 0. I would do that first. Then I would look at my amplitude, which is 2, and I would go up 2 units and down 2 units. So from 0, I would go up to, and I'll label this in blue, up to 2 and down to minus 2. Next, my period is 120. So I would go to 120 and divide it into 4 equal sections. So here's 120. I'll do this in purple. Here's 120 divided into 4 equal sections. So this would be 60, 30, and 90. And then I would draw the graph, and I like, take out a tiny eraser. Graph starts at a maximum. It's a very big dotted graph. Normally my dots would be more of them and more spread out. But can you see that the red graph is saying I'm starting at the maximum, and then I would go to the next ticking mark, maximum, center line, minimum, center line, maximum. That would be my graph without the shift. So usually I draw my graph without the shift with the dotted line first. That's the red one. And then I can take into account the shift. And the shift would say, I'm going to move every single thing 60 degrees to the right. 60 degrees is right. If 120 is right there, my 60 degrees is 2 ticky marks to the right. So can you see that this maximum point right here, 60 degrees to the right, moves now to a maximum point there. And you can either move all of your points 60, or if things work out really nice, like in this case they worked really nice to match up perfectly on a ticky mark. I could just go from this green point, that's a maximum, and say, oh, then I'll go center line, then minimum, then back, center line, then minimum, then center line, then maximum, then center line, then minimum. And you could do this by taking marks forever if you wanted. And it says draw for at least 2 periods, so now I went from 0 to 120 and back to negative 120, and I have 2 periods graphed. We can use this same DAB-C strategy to help us if we're given a graph. So in part C, we have the graph. From the graph, can you see where the middle line is? Okay, I think it's there. sometimes you think it's somewhere, and then it's a good way to check is, does it work for an amplitude to jump up and jump down? So if I would count here, I go up 1, 2, 3 to the maximum. Does that still work to the minimum? 1, 2, yes, 3 to the minimum. So I now found my d value, which in this formula is your k value. And I know my amplitude is 3. So that's going to be fine. I now know if I write out dab c as I'm going here, I figured out my d value is -2. I figured out my amplitude is 3, which could mean my a value is +3 or -3. I have some options. I can play around with this. My period. I can find a period from a graph by just going from maximum to maximum, or in this case, I would probably think the easiest thing would be to go from minimum to minimum, because then I jump from 0 to pi, and the math is really quite easy. How far is it from 0 to pi? My period is going to be pi. That does not mean my b value is going to be pi. Because you have two formulas. You have a formula that says, this is the one we were using before, that our period is 2 pi over our b value, but you can rearrange this formula, which means your b value is always 2 pi divided by your period. And if our period is pi, 2 pi divided by pi tells us our b value has to be 2. Now the dash c is kind of nice because it sort of is like a separation, that dash. The c value is going to change depending if you're doing a sine graph, which starts in the middle going up, or you're going to do a cos graph, which starts at a maximum. The c value can also be different depending on which maximum you use. So here for my cos graph, notice that I've got the 3 for my a value, I've got the 2 for my b value, I've got the -2 for my d value, and then I decided to use 0 as a c value and say no shift. But when I said no shift, I'm at the minimum instead of the maximum. So I made my a value a vertical reflection and negative. If you could have no shift, that's probably the nicest of that graph. I would say that's the nicest equation, because it has no shift involved. It looks the simplest that way, even though it has a negative in front, right? Mathematicians, if they can choose between a positive or negative number, they like positive numbers better. However, in this case, this would be the nicest graph. Now, if I was doing a sine graph, again, I have the same d value, the same b value, the same a value, and if I choose the positive a value, I need to find a place on my graph that's starting in the middle going up, if I'm using a positive a value. If I decided to use the negative a value, I would need to find a place on my graph starting in the middle going down. Now there are lots of places on this graph that start in the middle. There's my dotted line. Started in the middle going up. This is typically the most common one. You use the one that's closest to 0. Can you see that that is a shift of pi over 4 to the right? And so our c value, x's are liars, we write minus pi over 4 to show a shift of pi over 4 to the right. And these are two possible answers, but you could have an infinite amount of right answers. But don't guess, because there's also an infinite amount of wrong answers. And it doesn't come out to a 50-50 chance if you guess. Probably, like we're picking random numbers, would most likely get this wrong. Even though there's an infinite amount of right answers and an infinite amount of wrong answers. Okay. Now we're going to get to our 3 reciprocal trig functions. Do you remember their names? In English or in French only? Okay. First of all, there's this one. What is that one in French? In English we say cosecant. What do you say in French? Is it exactly the same? Yes? Or a little bit different? I didn't hear.
It's the same.
It's exactly the same?
With an accent.
With an accent. Cosecant. Okay. What about, then I'm guessing that you just go accent-wise on that one too? Okay. What about tangent? Is it just accented again? Oh, how boring. That'll be more exciting than that. We can use these identities that cosecant's 1 over sine, secant's 1 over cos, and cotangent's 1 over tan to graph the reciprocal function. Do you remember the strategy for graphing reciprocals? You first graph sine, then wherever you have x-intercepts, you get asymptotes. And then everywhere else, you just flip the answer. So for example, I know that on sine, from my unit circle, I have pi over 6 comma 1/2. That would mean on my cosecant graph, not necessarily lined up perfectly, but I'd flip the answer. Instead of 1/2, I'd have 2 over 1. I would have pi over 6 comma 2. And as a result, the best way to quickly graph cosecant is to say, well, wherever it's 1, which is here, here, and -1, sorry. 1 and -1, that's going to stay the same, because if I flip that answer and do 1 over 1, or 1 over -1, it stays the same. And then you just draw it towards the asymptotes. That's the quickest way to quickly draw cosecant, and the graph of secant is going to be the exact same strategy. Start with the graph of cos, and you have it there. See if you can draw in the asymptotes. The tangent one is the only one that's got a little bit of a weird thing going on. I'll put up the answer for your secant graph. You can see how you did. Again, just get your asymptotes. Wherever it's 1 and -1, those ones are going to stay the same. And draw it towards your asymptotes. And then what makes your tan graph a little bit interesting? Or sorry, your cotangent graph a little bit interesting. Here's our tan graph. Off to the side here, I'm going to graph cotangent. Cotangent, you know from your identities unit last year, is 1 over tangent. Cotangent is also what from your identities unit? Cos over sine. And technically, the graph of 1 over tangent x is slightly different than the graph of cos x over sine x. They seem like they should be identical, but there's a tiny difference in non-permissible values. If you graph 1 over tan x, your original asymptotes where tan is not allowed are still not allowed. Okay? Where is tan not allowed? Tan is not allowed when cos is 0. But if you graph cos over sine, then the only thing that's not allowed is sine can't equal 0. Cos could equal 0. And when we go to graph cotangent, okay, first of all, you will have asymptotes wherever tangent is equal to 0, because wherever tangent is equal to 0 is the same where sine is equal to 0. Those are your new non-permissible values. So your asymptotes for cotangent are at all of these x-intercepts. Now I'm going to just put big blue dots on these points. And highlight them over here. Technically, if you were drawing 1 over tan, those blue dots would not be allowed, because they're non-permissible values to begin with. If you have a non-permissible value, you can't all of a sudden make it permissible later. In the cotangent graph, those points are allowed. The difference between the graph of cos over sine, those points would be allowed. If you graphed 1 over tan, you'd actually have to have open circles there. And so mathematicians had to decide, what are we going to call the cotangent graph? Are we going to go with the cotangent graph as 1 over tangent? Or are we going to go with the cotangent graph as cos x over sine x? And they went with the cos x over sine x one, so these dots were allowed. So when drawing the cotangent graph, if I was using my tangent graph as a starting point, I would still go through, and wherever there's 1, and wherever there's -1, those points are going to stay the same. And if you make your asymptotes zeros, you now could have, whoa, okay. My connecting the dot skills sort of fell off over summer. I didn't practice them. There we go. Now I'm getting it. Oh yeah. And of course there would have been new asymptotes in here. And the reason I didn't originally graph everything on the same graph is because when you graph it all on the same graph, oh, it's looking busy. It's sort of like, math already hurts my brain and that hurts more. So, drew it separately, but I wanted to point out some of those key things. Okay. There's a note there at the bottom about which ones are odd and which ones are even. Cosecant and cotangent are odd, just like sine and tangent were odd, and secant is even, just like cosine is even.